and I will turn it over to Yaoguo Li, and let's go ahead and get started. Thank you so much for joining us online.
Great. Thank you so much, Sue, for that very kind introduction. And I've known Sue for many, many years, and just we always seem to kind of connect far away from our home institution. So it's great to be here, and also it's really wonderful for the invitation from SAGA, and thank you all the colleagues for joining. And let me share my screen. As you can probably tell that right now the geologic hydrogen is really kind of, I can call it a passion of me. And so for the group, we have a large team working on this. So per kind of discussion we had earlier with Stephanie, so I'm just going to repeat exactly the presentation I gave at Saga meeting late last year. So no changes and whatsoever, although there are updates that we'll be happy to can discuss during the Q&A session. So, Mano, you probably remember this, or you recognize this. These are two pictures from Namibia that was they were taken from the trip before the Saga meeting. And so the reason I want to show this is that kind of it's related to the presentation on geologic hydrogen. When you stand in places like it's so beautiful, so striking, but also you realize you're really immersed in the renewable energy, solar, wind. And years ago, like many of us, were just so convinced that the solar and wind would be the future. But slowly, because of the techno-economic analysis and the needed material for utilizing this forms energy, then slowly realize that's not necessarily the a viable path. And that's actually then one of the reasons that at least I got into the geologic hydrogen. So hopefully that gives context of thinking we are having. So title of my presentation is Geologic Hydrogen Exploration, an emerging role of mining geophysics. So really there are two aspects. One is geologic hydrogen exploration, the naturally occurring one, and then also the whole aspect of how the mining geophysics and mineral exploration geophysics really has a huge role, I would say, a more important role to play in this field. So my co-author is Dr. Mengli Zhang, and we've been a tag team working on this for the last few years. So I'll quickly go through a bit of background, comment on the hydrogen system and its relationship to geophysics, and talk about a concept that's really proposed by Mengli that is exploration around the source rock, or in her terms, original proposals in 2022 as the source rock centered strategy for geologic hydrogen exploration. Then we'll talk about the opportunities for mining geophysics. By inference, that's really the opportunities for the mining geophysicists. That's really what kind of part of my passion list. Then a bit of concluding remark. So background is there's a lot of charts like this you'll see flying around, but this particular one I like a lot from the it's from the U.S. Energy Information Administration that was put out in 2023. It's a projection of the electricity generation up to 2050 in the U.S. And in a lot of the places in the world, this chart is still valid, not exactly the quantitatively, but the makeup is still quite valid. So the key point in this is that the fossil fuel will remain a major energy source. No question about it. It's not going to be subtracted or replaced. But also renewable energy has been perceived to be the key for the future. But there are two major issues related to this kind of thinking. So one was the fossil fuel, one is the renewable. For fossil fuel, realize that there's basically the need to capture the carbon and store it. And of course, the economically now we realize that that is increasingly looking very expensive. And currently, it's mostly tax credit driven. And overall in the world, that is still the case. US, it's been changing. And the technical challenge is the how do you capture it? You can do point capture, that's actually much easier, but more distributed emission, it's really challenging to capture. Then, of course, long-term storage and monitoring. So that actually puts this aspect, it's not as rosy as one used to think of last decade also. The challenge with renewable is that, yes, there's a lot of those, but the issue is how do you store and transport that? Then that actually leads to one of the really weird phenomenon called the duck curve. Namely, you basically, currently the overall trend is the more renewable energy you put in the traditional grid, the more expensive the energy becomes, the price goes up. This concept was first discussed by California utilities, and the image on the top right shows basically this phenomenon. What happens is you need to maintain the base load. Then when you put more solar energy into it, that's during the day, you don't really have as much demand, then that got to be stored somewhere. And currently, it's not really feasible. Then when there's basically, eventually in the extreme case, it can destabilize the grid. So one of the solutions is that you store it in different ways. Right now, the most reliable way is the battery, but the issue is that you don't have enough metal. For mining geophysics, we're all aware of this. But there are two, oh, I actually should have updated this slide. There are two recent papers that actually highlight the issue that we're not going to find enough metals. Alan Jones in 2023 published a paper in TLE, which basically says the mining towards net zero impossible task. Uh, I really love this article by Jones. Of course, in the communities, there's a lot of controversial about it. Then more recently, last year, the three authors from ARPA-E and the DOE in US published another paper talking about the feasibility, both in terms of energy transfer and the metal. Also show same conclusion that actually metal and the renewable trying to make up for this is not really feasible. So that's actually then put the kind of tech step thing, what is really needed. So then one of, I would say my hero in terms of thinking is Jeremy Grantham of the Grantham Foundation. He noted in 2023 that if you look at the energy space, the geothermal is something that's near future. It will make a huge difference. In the immediate future, it's the he is convinced that's geologic hydrogen. And in the far future, it's going to be nuclear fusion. And what's interesting, he said nuclear fusion has always been said 20 years, 20 years. If it really is going to happen, then but in 20 years, by then the geothermal and the geologic hydrogen might have taken hold of the market, and then the fusion may not be relevant at all. So that's really interesting take. So the first part, of course, gets in the realm of geophysics, geoscience exploration, and Weian's group focusing now on the geologic hydrogen. So that's the backdrop of this. And the question is, okay, what is geologic hydrogen? Are there enough in the world? So, so let's look at evidence. There is the most prominent one, and that the one that set off this whole cycle is the Mali hydrogen well that actually exists for decades, and now it's actually generating electricity, powering a village. The hydrogen concentration here is about 98%. You go across the world, there's in the Oman, in Gulf of Oman, whole region, there's a semi-ophiolite. The salinization happens all over. And you go to the Oman, the hydrogen is bubbling out of water. And we, Mengli, myself, and the postdoc right now working in northern part of the ophiolite in UAE, and there's clear evidence there's supernazzation and the accumulation of the hydrogen happening. And the other interesting part that's more related to the mineral explorations, there's a really high-profile paper came out last year. It's chromite deposit in Albania, and 1 kilometer deep down, there is basically depressurized water, the hydrogen gas is bubbling out. And you look across in the US, there is Mid-Continent Rift, and in southern tip, now there's active exploration going on, and we're convinced there has been discovery, but the private industry is not talking about it. Then I should add that during the SAGA meeting, I'm talking to many geophysicists from Southern Africa, realized, and the geophysicists there are much more in tune in this whole thing, and many are already kind of staking land, doing exploration. So that's kind of evidence, partial evidence, and then then what generates the geologic hydrogen? Right now, there are the three mechanisms are considered to be the important ones. Synchronization, that's now understood to be a general term. There are more specifics within that. So basically, iron 2 rich mineral like olivine reacts with water, generates hydrogen and other minerals. Then radiolysis is basically radiation breaks down water over long geologic time, produce hydrogen. Hopefully, it accumulates, and that is a kind of a lot of debate going on with that. Then there's primordial or mantle sourced hydrogen that typically considered to be associated with deep cutting, cross-cutting fault. But what we're doing, and by and large, most of the community is focusing on the synchronization. So this is a map from Asgonic, published in 2015, just surface gas sampling all over the world. High enough ppm indicates the phenomenon is happening down below all over the world. And so I'm going to skip this one. This is bit dated. Only comment is that by all sorts of estimation, and slowly begin to be refined. One way is to estimate total volume of hydrogen, but that might not be the right way of thinking. But another way of thinking was just chemical potential. There's a lot of Fe2 minerals in the crust, but the projections there's going to be a huge market. Therefore, there's going to be a lot of exploration opportunities for that. So then in terms of the hydrogen, and this is a kind of modified version of a chart that Mengli put together 2 years ago, just explain to general audience what the different hydrogens. So most of us might have heard the blue hydrogen, the green hydrogen. Blue hydrogen is basically produced from steam reforming of methane. And the green hydrogen is electrolysis of water from renewable energy, hence the term green. And these two types of hydrogen serve as carriers, so basically equivalent to battery. But the geologic hydrogen, so one is naturally occurring, just as we discussed. Other part is actually we can stimulate the source rock and produce hydrogen. That is put together called in general terms geologic hydrogen. That is actually primary energy source. It no longer serves as a media to store energy and transport it to be used later on. But the geologic hydrogen is the energy source itself. So that actually changed the whole game completely. So with that, let's actually look at the one type of the system, as we mentioned. Most likely, the widespread occurrence would be ultramafic hydrogen system. In this, one of the basic equation that's been used a lot is this one. So you have on the far left is the Fe2 rich mineral, such as olivine in ultramafic rocks. When it reacts with water, it produces the magnetite, silicate, and the hydrogen gas. But now we understand there are a whole bunch of different types of alteration is going to be happening. And just synchronization is one of these that got attention and almost came in and took place of this name. And one other term we now is Mengli and myself use And we borrowed from some researchers from Australia. It's called ferrolysis, basically iron 2 mineral reacting with water. But this one still serves as a good equation to guide the thinking. So if you look at this equation, it's really interesting. The source rock, mineral exploration geophysics knows how to actually find them, delineate them, characterize them. We use EM, gravity, magnetics. The setting where the water reacts with ultramafic rocks, and we know how to look for it. Then, in fact, a whole gamut of geophysics methods can come in: EM, gravity, magnetic, and seismic. Right. So that's the setting. Then on the right hand side of the equation, we have the magnetite. We can consider that as to be an indicator of the synchronization process or ferrolysis process. Used to be, we think the magnetite content increases, magnetic susceptibility increases, but of course, you put in other reactions, magnetite can be destructed, and so there's complicated changes of susceptibility, but nonetheless, we can image it. Then this process also is volume expansion, so the density will decrease. That gives rise to the basis of gravity. And there's enough work in the physical property that's shown that synchronization decreases electrical resistivity. So EM comes in. Of course, then you go to the other end, that's target of the exploration, that's the hydrogen migration and accumulation. That's with seismic, the king of the basic exploration. Then gravity EM can come in. So that's why for us, this is really exciting. But also, I want to mention that you notice this is where really the whole system requires two branches of exploration: geophysics, traditional mineral exploration geophysics, and the exploration seismology. So expertise from mineral exploration, oil and gas exploration comes in. And that's why we feel that this is a huge opportunity in the energy space for the mineral exploration geophysicists to tap in. And let's just kind of think about what's the exploration strategy. As we all know, especially for mineral exploration geophysicists, got to zoom into where to find this. So for the last a number of years, gas sampling from surface and from legacy wells is one of the most used indicators. We call it surface indicators. But now it's slowly emerging that it's not necessarily a very effective way. In fact, Mengli has a beautiful example from published result by others to show this interesting offset between the surface gas sampling data and what's really happening in the subsurface. You think about it's actually almost obvious. And then what you do is others using general prospectivity map, and that's another approach. But then what we think is we really need to use deep looking geophysics and center the exploration around the source rocks for the reason that we're going to discuss a little bit down there. So exploration around H2 source rocks. This is a chart that in one of early papers Mengli put out that comparing the hydrocarbon and hydrogen system. The reason I do this is she spent a decade in the oil and gas industry, understand that system. That's where the generation rate is slow. The methane, natural gas, does not diffuse very much. It's almost, does not actually have a high reactivity. As a result, the reservoir and the source rock in the hydrocarbon exploration, therefore, you don't even need to consider in most cases where the source rock is. But in hydrogen, because of the fast generation rate and the very high diffusivity, because it's really small molecule and very high reactivity, then it's not expected to travel too far, accumulate in a faraway distance. So there's a proximity requirement between the reservoir and the source rock. Therefore, the best way we think is just look around the source rock and find synchronization, go around, look for the accumulation. So that actually leads to the understanding from our standpoint is that there is a spatial and temporal proximity requirement. We now understand the distances may be on the order of upper bound, couple hundred kilometers, that's far. Then we're usually talking about tens of kilometers. And time, it can be zero, concurrent, or within kind of several lifespans of human beings. So that's really, really short. It's like not on the traditional geological scale. And the other part is that because of this, source rock, the synchronization is interesting. It cannot be fresh, meaning an altered rock, or cannot be completely synchronized or spent. So somewhere in the middle. And in fact, uh, this presentation was given in October. Since then, in the last 5 months, we actually had quite a bit of advances. Now we understand way more what this stage requirement is. The other part, of course, we need, in terms of geological setting, hydrothermal fluid, and you need the favorable geochemistry. This is part that there's a lot research working on, but actually not getting to the system level. That's not what our team is working on. So we're actually trying to come up with a phenomenological description from geophysics side to fill in the gap for the geochemistry. And so the question is, okay, how do we do this? And the current understanding, at least from our perspective, is that the geochemical microbiology aspect of the hydrogen systems understanding has not got to the point that it can actually directly guide the exploration. Therefore, for us, trying to get this going and then make a difference is to rely on the phenomenological observation. So basically, the basis alteration of atomic rocks as common mineral deposit mineral system. This audience know this better than anyone else in the world in energy space. Therefore, we can leverage the existing knowledge from mineral systems. So that's actually what we're trying to do partly. One of the such examples is chromite deposit. What's interesting, this one I mentioned earlier, it came out last year, the chromite deposit in Albania. As most of you know, the chromite deposit almost exclusively formed through synchronization. And that's the same process actually that involved in the hydrogen generation. In this case, deep down about 1 kilometer, there's an accumulation of hydrogen. And there are several other cases you go across the world. There's this interesting, beautiful correlation between the presence of a chromite deposit and the hydrogen gas, as well as methane, where the methane has no business to be there in the traditional organic geochemistry sense. The understanding is that hydrogen reacts with the carbon matter, produces the methane that can serve as the indicator of the system. So then you look around the world, the ophiolite belts and that host the polyform of chromite deposit. It actually happens all over the world. This is partial map from I guess I missed the references from a recent publication that's all over the world. So that's actually one of the possible places that actually you can look for it. So you notice the top item there, that's where you've been kind of focusing on. So there's a lot of places, but this is only one subset. As I mentioned in the US, the Mid-Continent Rift, there's different types of atomic rocks, and they're exploring. So what's opportunity for the mind geophysicist? As I mentioned, you look at atomic rocks, look at synchronization. There's been a study characterizing the physical property change with the increased synchronization degree on atomic rocks. So basically, synchronization decreases the electric resistivity and it decreases conductivity and has this nominal increase of magnetic susceptibility. And this chart is a bit more complicated. We actually try to dissect this data set from the authors in Canada, trying to pull out more understanding. But the basis is that all these three physical properties would have actually dependence or relationship with civilization. And this example from her et al. In 2018 from chromite exploration settings in Tibet. And there they can clearly image the civilization zone within the ophiolite belt using the audio frequency magnetotelluric data. And so the notion is that we can put together the electrical, EM, radiometric, spectral data, and gravity magnetics data to image the source rock and also the civilization degree within source rock. So that's we see as the role of mineral exploration geophysics and opportunities for the mineral exploration geophysicists. So where are we? So we believe we have as a community, we have geophysical technology to delineate source rocks, including volumes and degrees of salinization. That centers exploration strategy. Then have technologies to delineate reservoirs. And interestingly, because of special properties, Mengli is going to talk about next, I think, that the traditional soil seismic based method may not be sufficient. That's where the geophysics method we use in the mineral exploration, such as gravity, borehole gravity, EM, will come into the risk. And we believe, at least for next half a decade, before the geologic hydrogen systems understanding matures, we actually have the phenomenological description of the system to guide us. So many challenges remain. So from what we think is that the components of system that can be imaged by geophysics, that's where the active research going on. And one other part is that it's more of a thinking, a big announce. The way we pose this question, how much should we migrate our mindset from petroleum exploration to mineral exploration? And that is actually happening. But by and large, a lot of the hydrogen exploration industry still thinking in terms of traditional exploration model or paradigm in the oil and gas. But that is changing. We see more and more people or the groups thinking in terms of the parties part, the mineral systems guidance. So to us, we think the intersection where this is going to happen is the mineral exploration, geophysics, and oil and gas exploration. That's where we can cover both ends of the system. So with that, so this is still same slide. Riz and Kathy for our invitation to SAGA. I would like to add that thanks Stephanie and Oleg, Sue, everyone for your invitation to present this again. We're passionate about this, and we hope more people want to join in to make this happen. So part research is supported by a consortium we have here. Mengli is leading the geophysics aspect of that consortium. I'm just playing along. So consortium name is Potential for Geologic Hydrogen Gas Resources. And we have the other consortium that's mining and petroleum exploration. That's where we develop methodologies we use in this research. So here's a quick list of the sponsors. With that, then of course, our emails here. So you have questions after this, feel free to reach out. With that, I will stop. And I ran a little bit over time. Sorry about that.
Oh, that was wonderful. Thank you. I was one of the people that had to miss your talk at Saga, so I was pushing for it to be given here. So I really appreciate you repeating it. That's so wonderful. And we'll move on to Mengli Zhang right away. I think it'll be better to just take all the questions at the end. Otherwise, we'll get into a big conversation and never get to the second talk. So over to you, Mengli. Thank you so much.
Yes, thank you. Can you see my screen?
That looks fantastic. Thank you.
Yeah. Thanks everyone for your time. My presentation title is Geologic Hydrogen Exploration and the Influence of Reservoir Diffusive Zone. So Yaoguo has talked about the different the color represents in the different hydrogen. It's important to know that what's the difference between geologic hydrogen and the blue hydrogen and the green hydrogen. This is a good summary for comparing the different colorful hydrogen from energy source and processing and different emission solutions and the role of hydrogen. As Yaoguo mentioned, hydrogen is energy carrier or equivalence of battery for the blue hydrogen and green hydrogen, since the energy source for them uh, is from a fossil hydrocarbon or wind, solar, and then the emission solutions some different. It's a positive CO2 emission for blue hydrogen, and we know it's net zero CO2 emission for green hydrogen. And I'd like to emphasize the role of geophysics can work is different in these four catalogs of the hydrogen. For the geologic hydrogen, we have the gold hydrogen, orange hydrogen, or white hydrogen. We would like to call them natural hydrogen and stimulated hydrogen. For the natural hydrogen, it's similar to explore subsurface accumulations, and we have no extra processing to get the stage of zero CO2. For the stimulated hydrogen, definitely we need the stimulations, no matter chemical stimulation or physical stimulation like fracturing. But it's possible to get the negative CO2 for the stimulated hydrogen. For both natural hydrogen and the stimulated hydrogen, hydrogen is a primary energy resource instead of the battery function in the blue hydrogen and green hydrogen. For the geophysicists, we can work on characterize the reservoir or the source rock in the natural hydrogen the area, and we can work on the monitoring stimulation and extraction, the processing for the stimulated hydrogen. Here is a brief outline for my talk. I'll start from the reservoir model and stimulation in geologic hydrogen, and then to present the reservoir property analysis and the diffusive zone. At last, I talk about some false negative or mitigations. We can use gravity data or MT data for the geological hydrogen. As Yaoguo mentioned, the geologic hydrogen exploration from the surface, like soil sampling, and in the large, like basin level scale to explore geologic hydrogen. However, when more and more research done, and the surface exploration is not accurate with the subsurface accumulations. Here is a good example to show that what the surface concentration looks like and what the subsurface structure and accumulations. For the surface exploration, the peak area from the geochemistry, the soil sampling. However, we saw that the subsurface peak area from geophysics about the accumulation, they are not in the same locations. So for the surface, it's good to identify the large area, like the basin level. But for the zoom in to the exploration, even to the drilling locations, definitely they are not consistent. That's why more and more work focuses on the geophysics and the subsurface. We have in our research group, we have a full spectrum of geophysics for the hydrogen explorations, from remote sensing and to the CSEM and the seismic and the mag or gravity or MT. For the different geophysical methods, there are the different depths of penetrations. It's just a physical theory that to explore the different level or the different target source rock or the reservoirs for the geologic hydrogen exploration. Here is a cartoon demonstration for the natural hydrogen using the ergodic geophysical survey design. Ergodic geophysical survey design is an efficient, irregular the survey design for the geologic hydrogen. We can use the airborne magnetic or the AGG for the exploration. We can also use MT to image the subsurface, both source rocks and the reservoir. And for the reservoir, there are two types. One is the structure trap for the hydrogen. The other is the lithology reservoir for trap the hydrogen. For the faults, the structure like the gentle faults, the trap of the hydrogen, seismic can works. But for some situations like the lithology, the trap for the reservoir, seismic may give a false negative result, which means that the reservoir may be existing, but just cannot be seen by seismic data. In that case, there is a mitigation using like gravity data and the MT data to help to identify if it's nothing there or it's the possible the reservoir there. Here is an example from the Mali site. We use their physical property from the well logging data from the Mali site. Here on the left panel, there is a summary on the density and velocity for the surrounding rocks and the hydrogen-rich rocks. We can see there's a density change about 5%, and also the velocity change about 25% in that area. And then we did numerical simulations for reservoir, like in these situations, we plotted on the red panel, like here. And then we did the simulation about the seismic profile to what it looks like for this lithology change for the seismic simulation. And on the left is the impedance inversion result. If all is correct, we can say there is the reservoir there. But however, we will show that this modeling has some incorrect assumptions for the geologic hydrogen. That's because the hydrogen system is different from the hydrocarbon system. In the hydrogen system, there is different generation rate. For the hydrocarbon, it's slowly generated, may take millions years, and once accumulated there, it's stable. Almost nothing change, and waiting people to explore extraction. But the hydrogen system, it's dynamic, which means it can generate fast. It's in the years, decades level to generate for the natural hydrogen. And we have collaborate with other teams on the stimulated hydrogen. It can be hours different if in the situation with the right catalyst. So that's totally change the geophysical exploration strategies. If you know that it's almost stable for the lifetime of the thousands of years for the hydrocarbon, but it can be changed the years, even the weeks, months for the hydrogen. So that really change the exploration strategies. We have to consider the hydrogen generation time window in our lifetime. And also there another characteristic difference for the hydrocarbon system and ultramafic hydrogen system. For the diffusivity and reactivity, hydrocarbon is stable, almost no change. But for the hydrogen, there is a high diffusivity and reactivity. There is also in terms of the time scale, what happened in the timeline and spatial in the distance for the hydrocarbon exploration. The reservoir can be far away from the source rock after the hydrocarbon migrate from source rock to far locations to the reservoir. Therefore, we have compared the reservoir publications and the source rock publication. Almost 90% of the publications or research focus on just the reservoir. But it makes sense since they're far away, no influence, or you don't need to consider the source rock. But for the hydrocarbon exploration, we definitely need to consider both source rock and the potential reservoirs, because the two locations for the reservoir and the source, they are close, and because the diffusivity and reactivity, the high probability for the reservoir it's near the source rocks. Then let's observe the influence of the transition zone on seismic signatures. This is hydrogen accumulations in the Mali wells, and we can observe the red area. So the hydrogen has a diffusive zone in their distribution, the vertical distribution. And for the hydrocarbon, it's sharp. So it's reasonable and plausible for we build a hydrocarbon model with a cap rock on the reservoir with a clear boundary. And then we run our simulations to test our geophysical method. However, when we work on the hydrocarbon model, and there is a potential for the hydrocarbon model, the diffusive zone existing between the cap rocks and the reservoirs. This is a situation for the lithology reservoir. Definitely, if the reservoir is the structure reservoir with faults, that's for that simulations, it's okay use a clear the boundary between the cap rock and the reservoir. I just talk about the situation for the lithology reservoir, the diffusive zone existing, and then build the correct model with diffusive zone, and then test the geophysical method should be considered in your testing and the model. Then I come to the seismic simulations with two reservoir models, the same volume without and with diffusive zone, what the seismic simulation results looks like. So on the left, it's the seismic simulation imaging without diffusive zone, and on the right, it's the seismic simulation with the diffusive zone. We can observe there is a clear the bright spot for the seismic in seismic events when we build the model without the diffusive zone. However, in the hydrocarbon, the diffusive zone probably be present, and if for the seismic, we may get a result like the right side. So it's not clear or obvious seismic signature in the imaging. So it may cause mislead us to a result that there is no seismic signature and there is no hydrogen reservoir there. That may be because the diffusive zone influence the seismic detection. It doesn't mean there is no hydrogen there. So we need to combine with other methods to identify if there is a hydrogen accumulation there. And that involves the false positive or false negative in the situation. So sometimes if the two reservoir model, like a small volume reservoir with a large volume reservoir with diffusive zone, you can say even for a small reservoirs, but it's clear the boundaries there, the seismic shows the significant the signal seismic signal there. But even a large reservoir with the diffusive zone, it may mislead that nothing there. So this impedance inversion to show the clearly if what the seismic signature or without signature can lead to different interpretation for the hydrogen reservoir. And last, how we provide some solutions for this false negative and to how to mitigate using gravity data. For the surface gravity data, we have done the simulation, and we can say the gravity data can give the interval result to show the density change at that area. If there is a possible density change, even the seismic signature is not obviously, but we still treat it as a potential accumulation of the hydrogen there if the source rock is nearby. And then we also have done recently for in the UAE area using MT data to check the salinization degree change and the possible accumulations near the ultralight belt in the UAE area. So the multi-geophysics really can help us to de-risk about the interpretation for the geophysical data and provide the possibility if it's less possibility or increase the possibility about the hydrogen accumulation. This is a different component for the gravity data, and we predict. So borehole gravity also the possible for us to identify the density change around that area, and then to make to predict if there is the hydrogen available there, if there is a borehole nearby. Here is a simulation. If there is a two borehole nearby, and we didn't touch or the drill to the hydrogen reservoirs. If we need to drill more or not, if in these situations, if we can make a decision that there is no hydrogen reservoir there, and we can deploy the borehole gravity sensors then to do the borehole simulations to check if there is a density anomaly around that area, and then to help us to make decisions if we drill more or the hydrogen accumulation in that area. So for the hydrogen reservoir, the seismic imaging indicate the potential, but no obvious bright spots. Gravity anomaly can mitigate the false negative and assistant to identify the hydrogen reservoirs. So If you would like to mitigate risk for your next drilling problem, we would recommend the borehole gravity to do the next step, and it can help you to decide which model is correct. There's a potential hydrogen reservoir between your borehole drilling, or there is not. Here is some takeaway message. So seismic data can predict the trap structure and lithology. False negative may exist in the seismic result. The ground and borehole gravity, now we think the MT data results can assist to identify the hydrogen reservoir. Thanks for our sponsors from the potential of geologic hydrogen gas reservoir. Here is hydrogen GIP members. Thank you so much for your time. I'm happy to take questions.
Oh, that's fantastic. Thank you so much, Mengli. It's really good to see you. And I guess you're in Washington, D.C., so that's one of my favorite towns. We've had a tremendous chat going on also on the side a little bit about some new results. So it sounds like South Africa's on the map too. So I'd like to take questions from people who are online at the moment. I think the best way to do that